Welcome back, everyone. So let's get started. So today we're going to be talking about k-means clustering, and and in particular Lloyd's algorithm for it, which is the most famous algorithm. So I'm just curious of those who's here, who's thinks they've seen the Lloyd's algorithm before. Okay, great. So I always so it always changes over the years. Who knows what's and what's kind of well known coming into the class. So great. So this so hopefully is new for for everyone. So it's a pretty so it's going to be kind of a different algorithm than what we've seen before in this class, but it's again going to have some iteration to it. So it'll be kind of like gradient descent in some way, but it won't be as nice as gradient descent. It's more tricky because of the combinatorial nature of clustering. So before we get started, yeah, so well, homework 5 was due today. We will have homework 6 out by Monday, hopefully, and that so that'll be the last assignment. So it's good. And then quiz 6 is not till next week. So I think we're okay. Hopefully homework 5 was not too bad. Hopefully some of the first few questions made you think a little bit, but once you got them, hopefully you understood stuff a bit so more deeply. So, okay. Yeah, so we are focusing on this type of clustering called assignment-based clustering. Okay, and the most famous version of this is the k-means formulation, which we'll talk about. But we will be talking about an input, which will be X, and this is our data. It's going to be a subset of RD. So we're going to think of, we nicely have these points, which are already vectors. And in fact, we also have a distance between these vectors. Right, so it's going to give us a value which is positive. And in fact, we will use this distance between X, any 2 points is going to be the Euclidean distance between them. And we're also going to get, as part of our input, a value K greater than 1, which is going to be the number of clusters that that we want. So, okay. So, and then within assignment-based clustering, the output of the clustering, the output of the algorithm is just going to be a set of k sites. All right, and so in the last class on Monday, I kind of changed. I started writing down some notation, which I think was non-optimal, did not match the book. So I'm going to go back to notation where S is going to be this set of the sites. And these are going to be, I'll call these lowercase s's, and these are going to be also subsets of RD. These are going to be points. So we're going to think of having these input point sets. This is our input X. These are points in just in R2. And my goal is to define these these sites, these are representative points. Right, so I want to find a representative points for these different groups of the data. And then this allows me to define this Voronoi diagram, which implicitly is going to group the points together. All right, so implicitly, there are going to be these subsets of these points. Okay, the subsets of the points. And so we are going to divide X is going to be equal to the union of J equals 1 to K of these sets Xj. Okay, so Xj will be a subset of X, and Xj equals the X in X such that this phi function defined on the sites maps to Sj, right? So Xj, so this set here would be X1, this set would be X2, right? So everything inside here, this subset of all the data points is X1, okay? This one X2, and so on. And we're working with this hard clustering, which means that Xj intersect Xj prime is going to be equal to the empty set for J not equal to J prime. Okay, so these are not going to overlap. Each point will have to be in exactly one cluster. Okay, so I'm doing a decomposition of the points into these clusters. Every point's in exactly one clustering. If I do a soft clustering, which we'll talk about next week, then I will get to relax this constraint a little bit. Okay, so I won't have to do this, and we'll see kind of the most common way how to do that. All right, so we're gonna again changing notation from the lecture on Monday, but this I believe should match what's in the book, and so I think this notation is a bit better here. All right, okay, and then specifically, we're going to be looking at the k-means formulation. Okay, and so that means our goal is going to be S star, which is going to be the arg min over these sets of sites where they're going to be exactly a size k. This will be a part of our input. Okay, and I want to minimize this function I equals 1 to n, and I'm going to look at the squared error. So that's xi mapped onto its closest site here, and I will call this cost of xs. Okay, so this will be our cost function. The cost function is this entire box here. The arg min will be the choice of S, which is minimizing cost. Okay, so we've, as is common in data analysis, to decide usually before you write down the algorithm, you say, here's some cost function I would like to optimize, and then we try and figure out an algorithm how to optimize this cost function. And so this means we have to trust the notion of the distance. The distance is encoded in here because that's this two norm between the distance between the point and it's assigned to kind of little site. We have to trust that this distance makes sense. And then this sum of the squared errors, which is a pretty common thing we're seeing throughout this semester. It's kind of the most common form, but it's not the only way to do this either. And we're also doing this assignment-based clustering where we're representing every cluster by a single point representative. There are some versions that don't try and do that and gives them more flexibility. If I do a single point representative, then I know I can use this function phi of s of x, which is the arg min of sj in s. an Sj of S that minimizes X minus Sj, right? So I'm minimizing, I'm mapping every point to the closest site. That defines this Voronoi diagram we talked about on Monday. And that defines any clustering that is this assignment base that uses these representatives. It has to decompose the data in this way. It has to follow one of these, that's by one of these Voronoi diagrams. Okay, and so it's more complicated than just the projection thing we're doing with dimensionality reduction, but it's kind of a well-defined geometry of what's going on. Okay, so this is the problem we're studying. And so we're decomposing the points, giving them representative sites for everything, and that implies an assignment onto them. Okay, so the question now we want to ask is, how do we solve for this, this kind of optimal S star, right? And so it's, there's gonna be a new algorithm we'll talk about called Lloyd's algorithm. And if you're in, it's called Lloyd's algorithm. If you're in an algorithms class, again, you're going to learn that you're given an input and you're given what an output has to guarantee to be. And then the algorithm is a method to get to that guaranteed output. Lloyd's algorithm is not going to have very real guarantees, very strong guarantees on the output. Okay, so a real purist in the sense of algorithms may not call this an algorithm. Okay, so it's going to be a method that's very effective for this approach, and it's mostly what people actually use to find a clustering. Okay, so let me describe the algorithm, and then we'll spend the rest of the lecture talking about it. Okay, so we want to initialize by choosing k points S, which will be usually a subset of X. Okay, so I'm going to choose, again, I'm given K as the input, as part of the input. I know I want K clusters. So I'm going to choose some subset S as a guess of the sites. And I'll usually use a subset of the data. So I'll pick K of the data points and say, this is okay, first guess, right? It's not almost never, and guess I got super duper lucky is going to be the right answer. But it's a guess, and then we're going to try and do some iteration and improve this, right? So the next step is going to be a thing that's going to repeat, and I'm going to iteratively try and improve this. And it's going to alternate between two steps. Okay, the first one is going to be pretty obvious. So before I said that anything that uses assignment-based clustering has to implicitly use this phi function that's mapping onto the closest point. But from the point of an algorithm, we have to actually do this mapping. Okay, so the first step is actually to compute this phi mapping. So I'm going to assign each xi to xj. So phi of s of xi equals sj. Okay, so so the first step is actually saying, well, I'm going to compute what is this phi mapping for each of the points and assign it into the cluster, which has the closest site, right? So remember, now this is the jth subset of X. So this would be a cluster. And this is the one associated with SJ, right? So I have these case sites at the top up here. So this implies that this is S1, S2 up to SK, right? So I have the case sites I chose to initialize with, and I'm going to assign each of the data points onto the one that's the closest. This is the one that's going to be the most logical assignment of the clusters given this head of the sites. Okay, but I want to optimize the site. I haven't optimized what the sites are yet. So that's what the step B is doing. Okay, step B is saying, well, now for all SJ in my set of these sites, I want to update SJ. And now this is the step that is why it's called k-means, that is clever about it and works with this for formulation. I can take each of these clusters, okay, and I'm just going to take so I'm just going to take the average. So I'm just taking the average or the mean of each of the clusters I found in step A and say, this is my new choice of the site. Okay, new choice of the site is no longer necessarily one of the data points. Okay, but that's okay. That's not what I was required. I have to be in, assume my data sets are in I can I can treat them as vectors. When I treat them as vectors, then SJ is just going to be a different vector in the space. It doesn't have to be one of the data points. Because it's the vectors, I can use the geometry of this to kind of pick a point that's in the middle, that's representative, and I'll just take the average of all the data. Okay, and so this is the whole this is the whole algorithm. So until it's converged, or I've gone for some number of R steps. And so this R might be 10 or 20. All right, so I'm just going to iterate between kind of assign everything to the closest site and then re-update the site as the average of all the points assigned to it. Once I've reset the sites in step B, I can go back to step A in this repeat, and now there might be some new assignments. These assignments may update because I've changed the location of the representative point, and this process can iterate. And usually I either can detect that it's converged into the right thing, or I say I've run for 10 or 20 iterations, and at this point I'm pretty satisfied, I'll stop.
So for step A, part of that would be to check which I guess xj is closest to xi.
What SJ is closest to XI, but yes. Okay. And so we talked about, it would be nice if we had a nice algorithm to quickly do this, but in practice, we can just compute the distance to each of them and find which one's the smallest. Right, so it's a pretty simple sort of algorithm. It's got a lot of, this is the main idea, and this is basically what was published by Lloyd. I mean, he wrote this when he was he was working at IBM Research in like the 1950s. And so he was sending signals across the channel. Okay, they were working in the 1950s was a long time ago. And he wanted to compress the data before he sent it across the channel. So he would compress it. And he was just doing this in one dimension. And he said, well, let's find some representative points and send those data points across the channel. And then his computer stopped working. Okay, so something like this. And they got a new computer and the instruction set changed. And his old code didn't run. And so he never actually published this. There was some manuscript or something. He published it not till like the 1980s. In the 1980s, said like, this idea is pretty cool. It works pretty well. And so they finally people encouraged him to publish it like in 1982 or something. Okay, so it's kind of an old idea. It's pretty simple. To get it to work in practice, there's lots of little nuances you have to worry about. But most things start with this, and then they do some tweaks for some weird cases that can happen. Okay, and so we're going to kind of talk through some of these issues, what we know about this algorithm, what can work, when it does not always work, and like sort of things you can do about it. But I'm not going to ask you to implement it. I'll show you there are versions built into kind of like any sort of software doing data analysis. They'll have a version of this that's built in, and it has a lot of these tweaks and nuances that they've handled. There are cases where you have ties you have to deal with and weird stuff. Okay, same way where we introduce the power method for doing the kind of to give you a sense of how you compute the SVD or the eigen decomposition, but actually implementing it carefully is like an at scale and accurately is like a big pain. It's not worth your time to do, but it's worth your time to kind of run it as use it as part of a process. That'll be kind of similar with this algorithm. All right, let me try and go through an example of how running this algorithm would work by kind of showing a geometric example of what the data might okay, so let's say this is our data kind of thing of this is the data X we're given as the input. Okay, and then we're going to start by our guess of the sites, and we're going to run this with k equals 4. Okay, so we're going to run an example of this algorithm where I'm going to pick 4 sites. Let's say I'm going to pick, this will be S1, this will be S2, this will be S3, and this will be S4. Okay, so it's not, these are probably not the right sites. Okay, but we want to see how this algorithm will work when we try and run this. Okay, and so we can start by thinking of how do we step A, right? I need to reassign the points on there, and we can kind of think of how this would work by drawing the Voronoi diagram here, right? We can think of where's this partition of the space. Okay, so it probably partitions the space up in this way. You kind of see that, well, yeah, I picked one that's a little bit too easy, but this one will probably converge very quickly. S1, okay, so everything in this cluster is assigned to S1, and there's nothing else. So I'm going to end up picking the mean point here as my updated S1. All right, so I'm going to move it to here when I reassign the mean. S4, similar. Move to the mean of this spot. S3, now it's going to move to S here. So it includes, its assignment includes some of the points up in this region and all of these. So it's going to be pulled down here from all these points. And S2 is going to shift just a small amount down here, right? Okay, so I've updated the centers. I think they've all pretty much moved where we'd want them to about. Okay, so now let's redraw the Voronoi diagrams and see what happens. And so so these are kind of shifting a bit here. And what's interesting is, let's say that the Voronoi diagram between S2 and S3 looks like this. So it should they should have these nice structure of intersection. Okay, and okay, so let's say the Bourdais diagram is here. And so it's pretty close to the right assignment. Okay, so S1 will stay here. S4 will stay here. There's no change in the assignment. S3 will move down to here. Okay, it's pretty close to the mean, but there's still kind of one point that's in the wrong spot here. Okay, and so S2 is going to move closer to the center here. Okay, and so then I will have to redraw these diagrams. Now it's going to look something like this. In fact, this line will continue there. Okay, right, so I've slightly adjusted things, and at this point, we're almost done. We're going to move this one a little bit here, and S3 will move a little bit down in the center. And now the rest of this will be about the same. Okay, so I'm going to kind of update these one step at a time, and if everything is working correctly, then yeah, and S1 and S4 will stay in the same spots, right? So these centers will tend to move to the middle of the cluster, and then as stuff gets sorted out around the boundary, the other sites will move towards the right areas, hopefully. Okay, so you kind of see it's kind of converging onto the right sites, and hopefully when there's a big group of points that has not been assigned, it will be pulling one of the sites towards it. And so it'll kind of converge, looks like it's converging it into the right place. Okay, so this is kind of a setting that works well. And so this is how you kind of think it should work. And a lot of the times it does work like this. Okay, so hopefully this made sense how it ran in this sort of picture. Okay, so it's kind of the sites are moving towards the middle. They're representing the mean. And once they're all representing the mean, at this point, if I were to run this again, there would be no update in which point is assigned to which site. They're all assigned to the same sites they were before. So if I recompute the mean, it's going to be in the same location, and nothing has changed. Okay. So this seemed to work. Okay, so can we say, does Lloyd's algorithm always converge? Does this always converge, or can this get stuck in a situation where it's like cycling between these different assignments? Okay, when you have an iterative algorithm with gradient descent, we knew it was always going down, and if it was a convex function, it would always find the single global minimum, and that's great. Okay, with the power method, it was not a convex optimization, but we could find kind of a similar sort of property. It was always converging, and unless it started in these unique positions where it was exactly one of the other eigenvectors, it converged to the top eigenvector. Okay, does that always happen here? Okay, this is a little bit more complicated. So the general answer is going to be, yes, it converges, but it's not necessarily always going to converge to the right answer. Okay, so let me explain what I mean by convergence. Okay, so we're going to write down this cost function x of s, and the only thing we're optimizing, okay, this is what we're optimizing. We're optimizing the choice of s, right? X is fixed. X is defining the cost function, just like when we had regression and we were optimizing over the parameters, the data, the input, that's fixed, that defines the cost function. Okay, and remember the cost function can be written like this. Times the distance from x to the assignment onto the closest point. Okay. Right, so this is our cost function, and we can rewrite this cost function. It's convenient to write it. We can write it as the cost per cluster, or per site. So for each site, we can look at X in Xj. So for all the points that are assigned to each Sj, we can look at Sj minus X squared. Right, sometimes it's useful to look at this. Okay, now because every data point is assigned to exactly one site, I'm still summing over all the data points here. And the point I'm assigning it to is the closest point, right? So this is the same cost. Okay. And so now we can see what happens. Now the claim I can make, so the claim is each step A or B decreases this cost XS. Okay, so decreasing this this cost function. If I read it this way, I've kind of pulled out the assignment step. I'm saying I'm going to assign it to the site it's assigned to. Okay, and that assignment could be changing. It's not always the closest one. That happens inside of A. And so technically, always it's not it's not necessarily decreasing, but does not increase. Okay, so you have to be a little bit, it might stay the same. Okay, so it might not, so when it gets to the final solution, it's not going to change anymore. And maybe one of the other steps it might not change, but we'll have to we'll work through this carefully. Okay, so this claim, let's look through these two steps. So for step A, right, so I just need to say that this cost function is going to decrease every time I run either of the step A or B, right? So for this, for all X, for all X in the data set, I'm going to assign to Xj, so phi of S X equal Sj, and this is the closest site, right? So I'm mapping it to the closest site. So if I look at this part of the cost function, change its assignment to a different site that's closer, right? Then that component, right? So if I look here for step A, so if I'm assigning it to a point that's closer, then this has to decrease. Each of the data points in all of X, it's assigning to a site that is the same or is decreasing, right? It's either the old assignment, but the old assignment may no longer be the point that's the closest. Okay, so if I change the assignment to the one that's closer, this cost function has to decrease, or it could stay the same. Okay? Hopefully this makes sense. And then for step B, remember, this is for all all of the sites. I'm going to set Sj equals to right as the average. I'm going to set the site as the average of all the things assigned to. So I'm not changing the assignment here, but I'm changing which is the average. So set to the average, and now I can look specifically at this part of the cost function. So when I look at step B, I'm going to look at this internal part when I've rewritten it. I only have to worry about one site at a time, and I'm just picking the site Sj that's minimizing the sum of the square root. Okay, and we can, and so I've told you before, and maybe we can look a little bit closer at this, but this is is kind of R min of all the points S. Right, so this is actually going to be the point that's minimizing of all the points S and RD, right? That's minimizing the sum of the squared distances. So that's, so what I want to set it to is the point that's minimizing the sum of squared distances. Turns out that's exactly the average. Okay, so the average is the thing that's minimizing the sum of the squared distances inside that purple box and that rewrite of the expression. And so it has to decrease the cost. It's the minimum possible point I could set for just everything inside this box. So that is also decreasing the cost. Or if it doesn't change, it's staying the same. Okay. And so we had, so that means that both of these iterations are decreasing the cost. So that means that if I walking through this iteration, the cost can only decrease or stay the same. So assuming that I break ties in a way which is consistent, okay, so if I come to the same situation, I always have a deterministic output for it. That means that I cannot come back to the same subset of these sites more than once. I can't come back to the same location of the sites more than once. If I saw a set of sites, I took a step and I changed them, the cost must go down. All right, so I must have, so it must be that so if I'm going through, you know, the set of sites 1, then let's say J, so at some time t plus 1 time t plus 2, then I must have set of, so I claim that ST cannot be equal to ST plus 2, okay? Because S of T of, because I have that the cost of X of ST is greater, let's say, assume there aren't any ties, otherwise I would stop, is greater than cost of X ST plus 1. Okay, and this means, and also cost of X ST plus 1 is greater than cost of X of ST plus 2. Okay, so that means that cost of X ST is greater than cost of X ST plus 2. And so that means S of T cannot be equal to S of T plus 2. Okay. So because if the cost is less, then they can't be the same, means that after I leave a location for a set of sites, a certain parameter, I can't go back to that set of parameters. Okay, so I don't have like convexity. That means that I can use that to say I'm always decreasing, or I'm not moving like in the, it's hard to, I'm not writing down the gradient and moving in the negative direction of the gradient, but I can say the cost is always decreasing. Okay. Okay, so I know I'm converging, right? So if I go back to this answer, does Lloyd's algorithm converge? Yes, it converges, but does it converge to the optimal solution? Okay, and so the answer is that no, it does not converge to the optimal solution. Or not, it might, but it doesn't have to. Okay, so Lloyd's algo may not converge to the optimal solution. So it converges, but not to the optimal, not necessarily to the optimal solution. Okay, so let me show an example here of how this could happen. Let's say I've got my input set might be like this. Okay, and so I'm going to say that K is equal to 4. And now I'm going to pick some sites here. We're going to pick S1 here, S2 here, S3 as one of these in the middle here, and S4 here. Okay, let's draw the Voronoi diagram of these. Okay. So what happens if I run one step of Lloyd's algorithm? Maybe I didn't draw these S1 and S2 perfectly, and maybe I can redraw them a little bit more here. Okay, so maybe I could put them so they balance these two splits, but I'm not going to update them. They're now on the average of all the points that they are representing. S4 is also the average of all the points it's representing, but this doesn't look like the best answer, right? So this is kind of this would be called a local minimum. Okay, and so if Lloyd's algorithm gets to this configuration, it stops. It does not know what to do. Okay, so it is no way to further iterate. It can't move the sites with respect to the current assignments, and it doesn't know how to change the assignments to make it any better. So neither of the two steps it can do is going to improve the cost function. So at this point, it's going to stop. It'll say, I'm not moving anymore. You might as well stop running the iterations, or you can run for 20 steps if you want to, but it's not going to make any difference. Okay. So there's a different optimal configuration, and it's not going to be this one. Okay, so it's converged to something, it'll stop, but it's not the right answer. Okay, so this is kind of disappointing. Okay, so it's okay, and this can actually happen, right? This is not so unusual. And kind of the more sites you pick, the larger K is, kind of the more likely this is to happen, that you somehow get one cluster gets too many sites, another one is split, one site kind of splits the two, kind of is playing the two clusters, but it doesn't know how to get from here to here. Right, at least the algorithm as I described it does not know how to do this. Okay, so how to address this non-optimal convergence. Okay, so so what should we do? All right, does anyone have any ideas? Let's go through and think through what we could possibly do here, and there are probably a bunch of right answers. So select which K points at what stage? Great. So try more initializations. Okay, and so if I just pick the same K points to start with, it's not going to work. So how do I make sure it's a different initialization?
I would just in relation to that, repeat the algorithm a certain number of times, randomizing which points you pick for your initialization.
All right, great. So try more um, um, more initializations and do this at random. Okay, so that would say common thing to try is step 0 is select S subset of X at random. Yeah.
You can also say like, put a basically if you select a point, that'll have.
Oh, okay, so I want to push the sites far apart from each other.
Yes, so
Yeah. Yeah, okay, great. So let me address the point. I want to say, so something about this first one first. So this is great. So this was the single most common thing 20 years ago, up until 20 years ago. This is what you would tell people. Just reinitialize at random. Okay. This can often work, but there are some fairly reasonable conditions you can find where if you do this, it will almost always, with very high probability, still give you the wrong answer. Okay, and these are quite reasonable things. If you've heard of it, if you've heard of like the coupon collectors problem, or if you think of like I'm trying to, so if I have k distinct clusters, they're actually k blobs of points, and I want to get 1 point in each of them, but it's set up in a configuration so they're all equally far apart. So if I don't pick one of the blobs correctly, I will always get stuck. And you can set things up this way. So I have to hit them exactly right. The probability of getting k points, each one in exactly one of the clusters, is actually a pretty low probability. And so there are lots of cases if k is fairly large, this will maybe get close eventually, but probably not consistently get close. All right.
what you said is like, yeah.
Okay, so initial. So you're saying, I want to get back to your point, but the other way would be to initialize where kind of each Sj is the average of some xjx subset. And so this choice is at random, right? So I could pick a subset of the points at random and then choose Sj to be its center. So start by splitting the data. What tends to happen here is you always get all the sites very near the middle. Okay, I'm going to pick a random selection, so I'm going to get some of each, and then they're all going to kind of average out. So if you think back to the central limit theorem, this is kind of an example where I'm taking an average. I'm getting a bunch of similar averages, and they're going to kind of average to about the same. So this will not get me a lot of diversity in the sense. Okay, so this is another thing. It's a very reasonable thing to try, but this one works worse than picking the sites at random. Okay, so you have this other point. Can you say what your other comment?
For each one of we have to make it so they company is consistent with range.
Great. Okay, so kind of force the sites not to be too close to each other, right? So force sites not too close. Okay, so this can be reasonable to do, but if my setting is such that I have 100 points here, 100 points here, and then I have 10 points out here. Okay, so if k is equal to 2, one option, or let's say k is equal to 3, the points on the right are more spread out. Is it better to have 1 point in the center of each of these cluster of size 100 or 1,000, and 1 point over there, but then these 2 points are close. Or to have 1 point here and 2 points out here. Now these points are not as close. Okay, so it turns out this one is better, and the red one is better, but these points are close, and I can set this up so they have to be close to each other. I may have a lot of points here, so I want to put more clusters in that region. So what is common to do is to say, if stuck and some points close, then randomly reassign to a far point. Okay, so I might randomly, I say, well, this right configuration, maybe it's stuck, maybe this is the right configuration, maybe not, I don't know, I can only look at my score. I say these 2 points are really close to each other, let me try throwing it out here and then run the algorithm and see if doing this does any better. Okay, and sometimes this works. Sometimes if I get stuck and I sense that 2 points are too close to each other, and there are other points that are far away from any of the sites, then maybe I'll throw it on to one of these other points. And I will try this and run it a bunch of times and keep track of the best cost, and then go back to whichever configuration had the best cost. I might be, when I first move it, I might be increasing the cost, but maybe it can converge to something else. And so kind of randomly splitting points. Something even weirder can happen. Sometimes xj will be equal to the empty set. So I might have a site that has no points assigned to it. Okay, so I can get so that it kind of is moved to the average of 2 clusters, but then those clusters get absorbed by something else. And then that point's not assigned any points. Well, then I would also randomly reassign this point. Okay, so this is kind of less common to do now because of configurations like this. And if I don't know, some of the data is more spread out, some of it's more clustered, and I might want here, but this we have to deal with. This is one of the weird cases you have to deal with in implementation. One of the reasons why I'm not going to assign you guys to try and implement this, because there's lots of these weird cases. Okay, so any other ideas? So these are some ideas, but these are not kind of the dominant ideas now. PCA in the day before we do the clustering. You can, and this can make the clustering run faster. Okay, it won't necessarily. Yeah, so because they're both sum of squared errors, these are fairly compatible. There's another sort of dimensionality reduction that works in really high dimensions called random projections, where you randomly project down. And this one you can say with guarantees, it will preserve what the clustering cost is. So you do dimensionality reduction, but this works in theory from like 1,000,000 dimensions down to 1,000 dimensions, and then you run it. And this is a good idea to do. With PCA, it's not a bad idea to do, but the arguments are more subtle of why this works. But it won't necessarily solve any of these issues. Any of these issues I can get them in a relatively low dimension. I can draw people have constructed all sorts of cases in relatively low dimensions. So this, unless I go down to 1 dimension, it's not really going to solve it. Yeah.
Would starting at something like a lower k work, and then you work your way up to like k equals 1.
Okay.
If you look at k equals 3, you randomly assign k equals 3.
Yeah, okay, so you're on the right track to what is kind of a better way to initialize. Okay, and so and the main idea that works here is to incrementally increase K. Okay, and they usually do it in a way that's not how you describe, where they run versions of Lloyds in between, but they just have a smarter way of choosing the initial K points instead of just picking them at random. And the other idea is you divide the points at random, and this doesn't always work either. But I can do something smarter of how to initially choose these K points. I want to pick points that are kind of far away from the points I've already chosen. Okay, so always far, always far from the existing sites. Okay, so the idea is if I have some data kind of like this, okay, and I happen to pick S1 here, and then I picked S2 here, then for S3, I don't want to pick it right next to X1. Right, so after I picked one or two of the sites, I say now I want to pick the next site, but knowing that I picked the first two. Okay, and there are two approaches to here, which we're not going to get into. One is called Gonzalez algorithm. And this is a just pure greedy algorithm. And this works for K-center clustering. This is the algorithm for K-center clustering. And that's minimizing the point that's furthest away from one of the sites. And I just greedily pick the point that's furthest away from all of my sites. Okay, so this is kind of, if you've seen Gonzalez algorithm, this should make a lot of sense of what to do, but it's not quite the right algorithm to do. The right algorithm is called k-means plus plus. Okay. Okay. And so this is built into most packages. When you call an algorithm to run some k-means clustering for you, it usually will initialize with k-means plus plus, and then it will run Lloyd's algorithm with these things to break ties, or if you have one of the sites that's nothing assigned to it, it deals with all these issues. Okay, and this one is randomized. Okay, I'm not going to fully explain how it works. It's a bit more complicated. It's kind of a combination of greedy and random at the same time. It wants to pick points that are far away, but it do so at random. Okay, and so it does this and it initializes, and because it's randomized, I can restart and rerun with the k-means plus plus in like more than once, and take whichever thing whatever initialization converges to the best answer, I keep that. Right, so this is kind of the standard way to, kind of the most common way to do this. Is to kind of randomly choose sites that tend to be far from each other, then run Lloyd's algorithm on top, and then pick whichever initialization will work best. You could still get into weird configurations that will converge to the wrong thing, but people have proven that if you do enough random initializations, you eventually find some run of Lloyd's algorithm that will converge to something nearly optimal, which is pretty good. It was kind of, it's complicated to show this always works, but you can make some argument about this. And so this is now pretty standard of most implementations will use this k-means plus plus, then they'll run Lloyd's, and they'll rerun this a few times. Okay, there's one more thing I want to mention, which is kind of related to what the best algorithms are in theory, but there's kind of a very simple version of this. And so your idea was, I'm picking too many K, so let me start with small number of K and then gradually increase the clusters. The opposite is to run with much larger K prime, much bigger than K, then combine them. Okay, so I'm going to run with a much larger K prime, hoping like K log K, right? So an extra log factor, if you've seen the coupon collectors problem. you kind of need to oversample to make sure you hit each of the clusters. So if you run with K prime, you're very likely to hit each of the clusters if you over choose K. And then once I have that, then I can pretend each of those sites is one of the representing a set of points, and then I merge them together. And this you can, to get this to actually work and argue that it's guaranteed to work is kind of tricky to do, but there's another line of work where you can do this process too, where you start by oversampling, and these algorithms will, if you do it incorrectly, they will run slower, so you maybe are a little bit cruder about it because the runtime depends on K, because I have to check each site where it's assigned to, but then I can combine them and I'm unlikely to miss one of these whole clusters. Okay, so these are kind of the other, some of the other ideas that people use because it can get stuck in local minimum, but if I play with these ideas, I can mostly get it to work. And so there's lots of this messy stuff happening under the hood. All right, okay. Okay, the main algorithm is pretty simple, and this is what I want the main sort of kind of takeaway from this lecture, to understand the main algorithm and then know that it doesn't always work. Okay, so you alternate between these two steps. You assign every point to the closest site, and then you update the sites. Okay, this is like a version. It's not quite, but it's like this more powerful method called expectation. So maximization. Okay, and these are called like these are called these EM algorithms, and they basically iterate between these two simple update steps where each of them is easy. So step A is easy, step B is easy. Trying to solve them jointly is hard, but alternating between these two kind of allows me to converge to something more complicated. And these EM algorithms are all versions like this. There are these alternating optimizations where there are two pieces I know how to solve. I don't know how to solve them jointly, but I can solve each of them individually, and I alternate between them. This is a very common framework for harder optimization problems. Okay, and our lecture on Monday next week, we're going to see mixture of Gaussians, where we're going to do a more complicated version of this. Okay, so this algorithm is the simple version. Mixture of Gaussians is the more complicated statistical version of this with soft clustering and everything, but it follows this pattern. And this is a very common pattern that you should kind of be aware exists. And if you have a hard optimization problem, try decomposing it into two or maybe more steps that you can each solve very easily. Okay, but also know that this does not always converge to the global optimum. It's not as nicely well constrained and defined as these gradient descent problems where we have this convex optimization. So it's very non-convex because of how the different parameters of the sites are interacting with each other. Okay, there's one more important point I wanted to talk about with respect to before we do that, just want to show you, I have a little piece of code linked off of here on what kind of sort of thing you would actually do in practice. You would use, this is, inside Python, there's this powerful library called sklearn. Okay, sklearn is a powerful library. And so we're going to use it for two things. First, we're going to use it to this function called make blobs. Okay, and people want to demonstrate how k-means clustering works. So they're gonna, what this does is it picks, in this case, I made 4 blobs, 4 centers, and I won 100 total points. And so I'm gonna pick some locations of the centers, 1, 2, 3, and 4 points down there. I'll scroll down in a second. And then I'm gonna pick some points from a random kind of Gaussian distribution. in this this two-dimensional space. So I've created 4 clusters. Ideally, what clusters look like. I pre-computed. I picked a good random state, number 6, because this gave me some reasonably well-separated clusters. If you rerun this with a different random state, then you think, okay, if I always pick 4 centers and pick Gaussian distributions around them, I'll always get 4 really nice clusters. Sometimes they overlap with each other, right? So you could have 4 clusters, but they just overlap with each other, and then it's not clear what the right answer for the clustering should be. Again, clustering is not as nice of a problem as we would hope it would be. Okay. But once I have this data, and this is an example of nice data here, then, and it's a clusterable data, then I can run this algorithm again inside sklearn. Right? There's a bunch of clustering algorithms. There's the k-means one. I'm going to run this with 4 clusters, and I'm going to call this fit function. This is going to do all the magic. Okay, and then I want to predict, and what it does for all the data points, it assigns it a label. Okay, it's going to assign it 1 of 4 labels. And so inside, when I called fit, that's when it did all that work, that k-means plus plus and Lloyd's algorithm with all the special cases. And now I can predict the centers. It also computes the centers, and I plot them different colors, different labels, and gives me this. Okay, so like you don't need to implement all this stuff under the hood. Just know that these algorithms exist, they're implemented, and they've handled a lot of these weird cases you don't want to deal with in practice. Okay. Okay. The last thing I want to talk about in the lecture today is this question, the input, some value k, the number of clusters. Okay, I'm going to choose k points here. Where did this value k come from? Right? Typically, you're just given a set of data points, and maybe you trust that the distance function you have works. Okay, but I also had to choose this number of k of how many clusters I should try and find. How did I determine what the right number k was? Well, every example I gave you, there were 4 clusters here, and I said, let's use k equals 4. Well, what if I choose a different number? Right here, there were 4 clusters. I ran k equals 4, but I might as well run k equals 3. If I ran k equals 3, this is probably close to the right answer. Right? So how do I know what the value k should be? Okay, so how to decide k. Okay. So again, let's look at our goal, this cost function. And again, this is okay. And so the first thing, if you're not sure what to do, you should probably try and run some experiments and plot stuff, right? I'm a big believer in trying to kind of plot stuff when you're unsure. And so what we're going to think to do is to look at the cost function. Okay, and I can run this for different values of k, and I can plot on the x-axis for k. So now, what's going to happen when I plot this? What do you think will happen? Will there be a nice kind of sweet spot, and that tells me where to pick k? What's this plot going to look like? It's going to look like this, and then I'll say, I should pick k here. Right? Is this what it will? Is this the right plot? No. Okay. Why not?
For me, one of the issues is technically if you make k large enough, the cost function will go down to 0.
Oh, okay.
Every point is its own. If it's its own, whatever, it will be that the cost is 0 because every point is its own cluster. not correct, but it's technically you minimize the cost.
No, that's right. That's right. That's exactly right. If I set k equals to n, the number of points, eventually it's gonna it's gonna head down to 0. Okay, so if I fixed it, and so I compute this for all k, I get a plot that looks like this, and I can pick. I don't want to pick that answer, so I pick this one. This look good? Is this how I choose k? Yeah, why would the cost go up? Yeah. So in fact, it won't. The cost will never go up for the optimal. If I solve it optimally, the cost will never go up. Great. So the cost always, let's put this S star, always decreases as k increases. Okay, so this plot is wrong. This is wrong. What the plot actually looks like will be like this, where it will eventually hit equal to some value 0, and it will always be decreasing. It will always be decreasing. Okay, great. So it can never increase like this. That's wrong. Okay. So it has to always decrease. Okay, great. So now how am I supposed to pick k? Now it's not so clear. It's always decreasing. The more I get k, the cost always decreases. So now I don't have a good way how to pick k anymore. Now I'm kind of in trouble. Okay. So, all right. So the common way to do this is, well, I'm going to redraw this purple. Let me try redrawing this green plot again. Make it a little bit more idealistic. Okay, so it looks kind of like this. So if it looks kind of like this, now maybe the answer is more interesting.
I was just saying, I guess, I don't know, it works. The inflection point where the rate of decrease is at a certain point.
Yeah, where's the second derivative change? Yeah, this is basically the right thing. It's a little trickier because I drew it as a continuous curve. It's actually discrete, but you can use discrete derivatives to probably do this. Typically, you would just plot it and then just look at it. Okay, and what's called the so what you would probably do is what's called the elbow method. Okay, is that, let me see if I can draw this well. You kind of think of like someone's arm happening here. Oh, picture was too good. It made me, okay, and then, okay, so think of someone's arm here, and this is the elbow. Okay, you kind of want to look for this kind of like someone's arm is coming down and then it bends at the elbow, and you want to pick it at the elbow. Okay. Okay, that's, yeah, very easy, very mathematical and clear, right? All the second derivative and everything. Yes, ideally you should use something like trying to beat the second derivative, look for the inflection point. But in practice, you kind of just plot it and kind of look at it and say, that starts to plateau. I'm getting diminishing returns after a certain point. Okay, and this is kind of what you want to see, where it goes down kind of sharply and then it kind of flattens out. Okay, and so there are indeed fancier methods how to do this. Okay, I don't think they work any better. Okay, this is what, if you ask me how to do it, I'll tell you, try plotting with multiple values of k and look for the elbow and do that. Where exactly is the elbow here? I don't know. Is it here or here or here? I don't know. It's about the same. again, this clustering is kind of like a dark art, and you know, so do you want a little bit more condensed with fewer clusters, or do you want a little bit better representation? It's, so it's kind of up to you. Okay, so this is the ideal thing of how it will work. This should be roughly how it will look if I look back to this example here, it will, as I increase K, it will come down pretty sharply, and then it's going to kind of plateau. I'm going to get diminishing returns as I go to 5. I'm going to take one of these and split it, and I'm not going to get a lot of return on this investment. It'll still decrease some, but it'll decrease a lot less. I want to try and, it's not always going to look like this. If my data set if this has one blob, okay, then this curve is going to look like this. Okay, so this one has no has no elbow. If it's just one blob and there aren't clusters, you're not going to see an elbow in here, and that's kind of maybe a good indication you're not finding very very well-defined clusters. Okay, where if it looks like then I'm going to get something that looks like this. Oh, this is off the bottom. So then K equals 4, and this will be about 4. That's going to look something like this. Be sharp, and it's going to flatten. It's fairly subtle, the difference between these two. You plot them, you kind of have to, I don't know, it can be, as the clusters merge closer together, then the purple curve will merge to the green curve. And so it's not always clear either. It's not always going to give you a right answer. Look, let me draw another picture. Okay, now how many clusters? Okay, so there's kind of two obvious answers here. So if I plot this, there's going to be 2 points here, one at 3 and another one at 9. Okay, and you're going to kind of get a curve that's going to look like this. It's going to kind of have 2 elbows, right? This is like a broken arm or something, right? Yikes. Okay, I'm not going to draw the arm on this guy, but there you can either say, what's happening here? Okay, so either I can say this is K equals 3, or alternatively, I can do K equals 9. Okay, and it's not clear which is the right answer. Depends on the scale that you want to look at it. 3 is a very reasonable answer. 9 is a very reasonable answer. All right, so who thinks the right answer is 3? And who likes 9? Okay, great. Good. So we had some people like each. That's the point, right? There's not, even in this case where there are these inflection points for both of these, there's not a clear right answer. It's kind of a choice of scale. This is, again, it's a modeling choice. There's not some mathematical right answer here. Okay. So with the mixture of Gaussians, there's a way to kind of, we can use, it fits better with the statistical modeling of it. There's something called Bayesian information criteria, which is kind of a right answer. We'll maybe I'll mention that in Monday's lecture. But again, it's still an imperfect answer, and there still could be multiple very good answers. It's hard to know which one is better. All right, so this is kind of, again, it's kind of nebulous in modeling. There are lots of these choices here, and it's kind of messy to use, but kind of, you know, this will give you the main guidance on what to do. So we'll stop here. Okay, I'll see you next week, Monday.